All right, these are the homework solutions for our constant velocity practice problems. So looking at this diagram here, figure 2.71, we're going to look first at A, which is this green arrow. So for number 1, first we want to see the distance traveled. So I'm going to look, I'm going to see, all right, A starts at 0 and it goes to the end of this arrow. So it looks like it travels a distance of 7 meters. B, so I'll go ahead and label this A. B is the magnitude of the displacement from start to finish. So again, I'm looking at where I start and where I finish, and this is the magnitude, so I'm just looking at the size. So the magnitude of the displacement, so it's just the size of the displacement, or the number value, is going to be 7 meters as well. Then C is just to distinguish between the magnitude of the displacement and the actual displacement. So if I look at the displacement, I'm going to calculate this, delta x in this case, as x2 minus x1. So x2 is going to be the 7 meter mark minus x1, which is the 0 meter mark. So my displacement for number 1 is just positive 7 meters. For number 2, I'm looking at arrow B, which is this purple arrow. So I'll leave this line here that I sketched about the 7, but B starts at the 12 mark. So the distance I can easily see, I go from 12 down to 7. So I'm going from 12 to 7. My distance traveled is just going to be 5 meters. Doesn't matter which way I go, just matters how far I go. Then for B, the magnitude of the displacement is just going to be, well, from 12 to 7 is 5, right? Or I can think of it in my formula as delta x equals my final position, which is 7 meters, minus my initial, which is 12 meters. Delta x in this case is negative 5 meters. Now the magnitude of this is just the 5 part. So it's just 5 meters. While the actual displacement, which it's asking for in C, is the same value with the negative included. For number 3, we have path C, which is this red thing that does a squiggle. So I'm going to go ahead and erase these other lines that I created. And we're going to have C start at 2, and it appears that it ends at 10, but it makes a little switcheroo here in the middle. So for A, we're looking at distance traveled. So let's see. I start at 2, and I go to 10. So that's 2 to 10 being 8 meters. Then once I get to the 10, I turn around and I go back to the 8. So this right here is from 10 down to 8. So that's another 2 meters. And then I turn around again and go back to the 10. So this is the 8 back to the 10, which is 2 meters as well. So I just put all 3 of these together, and I have a total distance traveled of 12 meters. For B, I'm just going to go ahead and calculate displacement. So displacement in this case just compares the final and initial points. So my final point is right here at the 10 meter mark. My initial point was here at the 2 meter mark. So I'll have 10 meters minus 2 meters, final minus initial, which is just positive 8 meters. So it turns out in this case that C, which is the actual displacement, is identical to the magnitude of the displacement that we got in B. Now for number 4, we're looking at D, which is this orange blob going on here. So again, I'll erase my lines, and I have an ending point, which is right here at the 5 mark, and D starts at the 9. So for A, I'm going to look at the first leg of this trip, which appears to go from 9 down to 3. So that's 6 meters. Then once I get to the 3, I seem to turn around and go to the 5. So from 3 to 5, that is a distance of 2 meters. So I put these two together, and the total distance traveled is 8 meters. For B and C, we'll go ahead and do both together again. Displacement is just going to be final position minus initial. So my final position is right here at the 5 meter mark. This is where I end. This is my initial position at 9. So I'm going to have 5 minus 9. So my displacement is negative 4 meters. So the magnitude, so really B, is just the 4 meter part, while the actual displacement includes the negative sign. So we have a negative 4 meters. And that's all there is to these. For number 11, we have a student driving to the university from home and notices that the odometer goes from 12 kilometers, or changes by 12 kilometers. So this just means that my displacement, or the distance traveled, really the distance, not the displacement, has been 12 kilometers. So I'm going to record this as my distance. I also know that it took me 18 minutes. So I'm going to say time is 18 minutes. I'll record that. So A asks, what is average speed? So average speed is defined as distance over time. And so for us, we have 12 kilometers over 18 minutes. So pull out a calculator and calculate this. But our average speed is going to be about 0.67 kilometers per minute. B says, all right, if our straight line distance from home to university was 10.3 kilometers in a direction 25 degrees south of east, what was her average velocity? So I'm just going to sketch this really quickly. So what this just means is my straight line distance from home to university is 10.3 kilometers in a direction that is 25 degrees this way. This information is not actually very important. We just need to know that we're not going in a straight line when we were talking about our total distance traveled. So maybe we made some turns and whatnot to get there. So from here, just to solve for for velocity average, we now want displacement over time. And so my displacement here is just comparing the straight line distance between where we started and where we finished. So points 1 and 2. So here, delta x is just going to be 10.3 kilometers over the 18 minutes that it took to travel this distance. So my average velocity, if I go and get a calculator, is going to be 10.3 divided by 18, which is about 0.572, and that's, again, kilometers per minute. Now C says if she returns home by the same path 7.5 hours after she left, what were her average speed and velocity for the entire trip? So this becomes a little interesting. So first off, we go the same path. So the total distance traveled will just be 2 times the 12 kilometers we went the first time. So this is total distance. Then the total time is going to be the total time it took the first time, times 2, this is just for the traveling, plus the 7.5 hours, and we need to turn that into minutes. So the way we do that is we say that we have 7.5 hours times 60 minutes per hour. So this part's a little tricky. So the total time, if we write all this out, is going to be 2 times 18, which is 36, plus our 7.5 times 60, for a total of 486 minutes. Now, I'll go ahead and do it because it's the second part of this, but the total displacement actually ends up being 0 because start and end points are the same if we go back to where we started. So our speed for the total trip is going to be total distance over total time, which is going to be, this is 24 kilometers, over our total time of 486 minutes, which is a very small average speed now. So plugging this into a calculator, we get 0.049 kilometers per minute as our average speed. And then our average velocity, which is delta x over total time, is actually going to be 0 over our 486. So our average velocity ends up being 0 in this case. And the units doesn't matter because 0 in any units is 0. For number 12, the speed of propagation, the action potential, which is an electrical signal in a nerve, depends on the diameter of the fiber. So if the nerve that connects your spine to your feet is 1.1 meters long, so let's say it's going to go 1.1 meters, and the nerve impulse travels at 18 meters per second, how long does it take for the nerve signal to travel this distance? Well, velocity, as we said, is delta x over delta t, or t. So if I rearrange this and solve for time, I can do that by first multiplying both sides by delta t. So that cancels out on the right and leaves me with this. And one more step would divide both sides by v and say that, all right, delta t is delta x divided by our velocity. So let's plug some numbers in. We have 1.1 meters for our delta x, and our velocity is 18 meters per second. Sorry, this should be delta t. Our time that elapses to travel that distance should be 1.1 divided by 18, which is 0.061 seconds, or about 61 milliseconds. That's how long it takes a nerve impulse to travel down your nerves. So number 14, we have a football quarterback that runs 15 meters straight down the field in 2.5 seconds. So I have delta x of 15 meters in a time of 2.5 seconds. He's then hit and gets pushed back 3 meters in 1.75 seconds. Then he breaks the tackle and runs straight forward another 21 meters in 5.2 seconds. So we have 3 different things going on here. And in fact, what I'm going to do is I'm actually going to label these with different numbers. So I'm going to say this is delta x1 and delta t1. This is delta x2 and delta t2. And delta x3 and t3. So I'll also label them with big numbers. So we got 1, 2, 3. So we have 3 pieces here. So for number 1, the average velocity for each interval is going to be v average is equal to delta x over delta t. So we're going to have positive 15 meters over 2.5 seconds. So for the first little interval, we have 15 divided by 2.5, which, if we pull our calculators out, is just an average velocity of 6 meters per second. Then for 2, our average velocity is going to be the same thing, but with delta x2 and delta t2. So this is going to be a negative 3 meters, because we're actually going in the opposite direction. So we have negative 3 meters over our 1.75 seconds. So our average velocity for part 2 is going to be negative 3 divided by 1.75, which is approximately 1.71 meters per second. I'm just going to round that. And then the same thing happens for 3. So we have delta x3 over delta t3. So that's going to be a positive 21 meters over 5.2 seconds. So our average velocity here, pull out a calculator, 21 divided by 5.2 is 4.04 meters per second. So there's the average velocity for each interval. Now we just want the average velocity for the entire motion. So if I think about this in terms of making a path that looks something like this, I just need to find the difference in position between these 2 points. So I go to the right 15 meters, I go back negative 3, and then I end up 21 more. So if I put all of these together, delta x total is going to be 15 minus 3 plus 21, which with a little bit of math just gives us 33 meters. Then we have our total time, which will just be the sum of all the times. There's no direction for it. So it's 2.5 plus 1.75 plus 5.2, and I need a calculator to do this. So we end up with a total time of 9.45 seconds. So V average overall, so this is just like the total V average, is going to be, so delta X total over delta T total, which is 33 meters over 9.45 seconds. So plugging this in your calculator, you get an average velocity for the entire thing of about 3.49 meters per second. So here's each piece, 1, 2, and 3, and here's the overall.